So today's webinar is about thermal conductivity. It's concerning which method should be used for which application, for which type of material. And this is a quite complicated topic, so that we will try to guide you through the jungle of measurement of thermal conductivity in this webinar. My name is Hans Marx. I'm today's speaker. Whenever you have any questions later on, you can write them by email to my address. You can do so in German, English, or French language, whatever you prefer. My colleague Erika Hahn, our application manager for thermal conductivity, unfortunately cannot join in today. But if you have any very particular questions concerning applications, you can write an email directly to her. So I will start with a short company presentation, give a short interview about thermal conductivity before I present different measurement methods and instruments. When this is done, we will talk about samples and materials and how to select an instrument for a certain application. And I will finish with a couple of examples how to select an instrument. So the company Linseis Messgeräte was founded more than 60 years ago by Maximilian Linseis. The actual owner and managing director are his son and grandson, and a further grandson is head of R&D. Our company is in Selb in Germany, and we have own sales offices in the United States of America, in China, and in India. And we are represented by more than 65 distributors throughout the entire world. More than 60 years ago, the business started with a big part of data loggers and so-called flatbed recorders. They are nowadays completely out of fashion, and we now focus completely on measurement instruments for thermal analysis, for the characterization of thermoelectric materials, and for the measurement of thermal conductivity. In our application labs in Germany, we do also service measurements. Our product range includes different scanning calorimeters, DSC, for the determination of phase transitions and chemical reactions, thermobalances for thermal stability and chemical reactions as well. These two techniques may be coupled in so-called simultaneous thermal analyzers. Furthermore, we manufacture instruments for the measurement of thermomechanical properties and length expansion by thermomechanical analyzers and dilatometers. We manufacture also analyzers to characterize thermoelectric materials and semiconductors by the Hall effect. Many of these instruments may be coupled to evolved gas analysis or are available in customized versions, for example, at very high pressures for more than 100 bars pressure, for example. But today's topic is measurement of thermal conductivity and thermal diffusivity. I will talk about bulk materials, but also a little bit about thin film analyzers. So those are the instruments I will present today, the instruments and the methods. The heat flow meter, HFM, the TIM tester, TIM standing for thermal interface material, the laser or light flash analyzers, LFA, the Transient Hot Bridge, THB, which is improved hot wire technique, and two analyzers for the characterization of thin films, the TF-LFA, thin film laser flash analyzer, and the TFA, thin film analyzer. So the thermal conductivity is measured in the units of watt per meter and Kelvin. And I showed a couple of different types of materials in this slide with their thermal conductivity. Please be aware this is a logarithmic scale. So the lowest thermal conductivities are found for insulation systems, with thermal conductivities usually much below 1 watt per meter and Kelvin. Gases also have very low thermal conductivities in the range of 0.01 to 0.1 watt per meter Kelvin. Liquids have quite low thermal conductivities as well. Usually hydrocarbons have a thermal conductivity in the range of 0.1 to 0.2 watt per meter and Kelvin, while polar solvents like water may have higher thermal conductivities in the range of approximately up to 0.6 watt per meter Kelvin. Mercury is an exception. It should be, the properties are in between a liquid and a metal. So compared to a liquid, it has a quite high thermal conductivity. Compared to a pure metal, it has a quite low thermal conductivity. Non-metallic solids have thermal conductivities ranging approximately between 0.2 for plastics and a couple of tenths of watt per meter and Kelvin for oxide and nitrides. Metallic alloys have higher thermal conductivities in the range of tenths to 100 watt per meter and Kelvin, and the highest thermal conductivities are found for pure metals, with the highest thermal conductivity being this of copper in the range of approximately 500 watt per meter and Kelvin. Thermal conductivity depends also on the temperature. So whenever you have select an instrument, you should be aware if it covers the temperature of your specific application or the application of your material. Heat flow meters cover quite small temperature range. TIM testers a somehow broader temperature range. The transient hot bridge even broader, from very low temperature to quite high temperatures. And the laser flash and light flash analyzers cover the broadest range from minus 125 to 2800 degrees, depending on the selected furnace. This range cannot be covered by one furnace, but by at least 2 furnaces. The thermal conductivity measurement range is the broadest for the transient hot bridge and for the laser flash analyzer. Both are able to analyze low conducting materials and very high conducting materials. So the measurement methods are separated in 2 groups, the so-called transient or time-dependent methods and the stationary methods. In a transient method, the sample is subjected by a short-term thermal disturbance, and then this disturbance is observed as a function of time during the propagation throughout the sample. The most important techniques for transient methods are the so-called hot wire or hot strip or hot plane methods and the laser and light flash method. The main advantage of the transient method is that they require only a short measurement time and cover a very broad thermal conductivity range and also a broad temperature range. The theory to get thermal conductivity out of the results is maybe quite complicated, but this is not the user's problem. But this is solved in the manufacturer's device and in the software for the evaluation of the data. Stationary methods are characterized that stable, no more time-dependent temperature gradient is established throughout the material. And this is achieved when the incoming energy equals the outcoming energy. So in this case, you are in a steady state. The important techniques are heat flow meters and guarded hot plates, and also the TIM tester is working according to a stationary method. The advantages are that the data evaluation is easy, the accuracy is high, but these methods need quite long measurement times in order to come to this steady, no more time-dependent state. The thermal conductivity and the temperature ranges for such method is limited as well. So let's start with the first method. It's a heat flow meter. It's a stationary method. And in this method, the sample is positioned between the cooled and the heated plate. So you have a heating, the sample, and the cooling. And between this heating and the sample, there is a temperature and heat flux transducer. And the same is on the opposite side on between the sample and the cold plate. And from the results of these temperatures and heat flux transducers, the thermal conductivity may be calculated by these formula. In an instrument, this is presented like this. In a schematic drawing, you will find the heated plate on top, a heat flux transducer, the sample, the second heat flux transducer, and the cooled plate. Heat flow meters are mainly used to analyze building materials and insulation materials. And for this reason, the temperature range is quite close to room temperature. Depending on the model, it is included in the range of approximately -30 to +100 degrees centigrade. The measurement range is restricted as well to quite low values as they are required for insulating and building materials. Typical samples are blocks, or like shown here for this insulation material, of a size of 30 by 30 centimeter with a couple of centimeter thickness. And they are positioned here behind this door between the hot and the cold plate. The second method I want to introduce is the thermal interface materials tester, the TIM tester. It works according to a stationary method as well. It's very comparable to the principle of the heat flow meter. So you have a heat sink, meaning it's a cold plate. You have a heat source, so a hot plate. The sample is positioned in between, and you find so-called meter bars between the heat sink and the specimen, and between the heat source and the sample. And from the result of these meter bars, you get the information about thermal conductivity. Additionally, you have a force which may be regulated, so you can measure the sample's properties depending on an applied force. And due to this controlled force, you can analyze also compressible materials, like, for example, these pads, which are used as interface materials. You can analyze pastes and even liquids. The data evaluation is done according to a certain American standard. And in this standard, it's specified that you should analyze the same sample with 3 different sizes, thicknesses. In this case, 3, 2, and 1 millimeter thickness. So the raw result of a TIM tester is the so-called thermal impedance. And if you plot this thermal impedance against the thickness of the sample, you get a straight line. And from the slope of the straight line, you can compute the thermal conductivity. And from the offset, you get information about the contact resistance. The first transient or time-dependent method I want to introduce is the most commonly used one. It's a laser or light flash analyzer. And the standard says that a small, thin disc specimen, the sample, is subjected to a high-intensity, short-duration radiant energy pulse, so a laser pulse. But it can not only be a laser pulse, but also a light pulse, usually done with a xenon flash lamp. And the energy of this pulse is absorbed on the front side of the sample. And the rear phase temperature of the sample is monitored by a thermometer, mostly an infrared detector. And from the signal from this infrared detector, the thermal diffusivity may be calculated. The setup is shown in this example. You have the sample positioned in a furnace. A laser light is hitting the front face of the sample, and the rear face temperature is monitored by this detector. And this is how the detector signal looks like. So it goes through maximum, and from this maximum divided by 2, you get the half height of the signal. And the time required to come to this half height is so-called half time. And this half time is used to calculate the thermal diffusivity. This is done by this formula. Thermal diffusivity equals a constant value multiplied with the sample's thickness squared and divided by the half time. So it's a quite simple formula. And if you want to calculate thermal conductivity out of the thermal diffusivity, you have to multiply with the density and the specific heat capacity of the material. So this laser and light flash method does not give directly thermal conductivity, but you have to know density and specific heat capacity to compute thermal conductivity. So the temperature range is very broad, depending on the used furnace. It's covered the temperature range of -125 to 2,800 degrees using different furnaces. The measurement range is very broad, from poorly conducting material to the highest conducting material, so that polymers, ceramics, and metals may be analyzed. Typical samples are such discs with a diameter often of 1 inch, so 25.4 millimeter, but they may be smaller, like for example 10 millimeter in diameter, or they may be square shaped. The thickness is usually in the range of 1 to 3 millimeter, and this thickness has to be well defined and well known, because you remind the formula, the thickness squared is used to calculate thermal diffusivity and thermal conductivity out of it. So typical samples are compact, homogeneous solids, but also pastes, liquids, and fine powders may be analyzed using some special adapters. The next transient method I want to introduce is a hot wire technique, the so-called Transient Hot Bridge, which is an improved hot wire technique. In these techniques, a wire is heated and it is surrounded by the sample, and the temperature is measured. And the temperature time curves contains all data necessary for the calculation of thermal conductivity. So this is the temperature logarithm over time curve, and from the slope represented in green, the thermal conductivity and thermal diffusivity may be calculated. The hot wire and the thermometer are usually embedded in a sensor, so those are typical sensors. They are made from a very thin polymer foil, and in this foil the hot wires and the thermometers are embedded, and the sample, in this case a transparent PMMA plexiglass sample, is covering the sensor, and this would be a typical setup to measure thermal conductivity. So the temperature range covered by the Transient Hot Bridge depends on the sensor type. The Kapton foil sensors cover a range up to 200 or 300 degrees, 200 under oxidative, 300 degrees under protective atmosphere. There are ceramic sensors available resisting to temperatures of more than 700 degrees. The covered thermal conductivity range is very broad. You can analyze insulating materials, but also metals. And the typical sample size depends on the used sensor. this active surface has to be covered at least. So typical sample size is a range of a couple of centimeters, square centimeters. The minimum thickness depends on the thermal diffusivity of the sample. The lower the thermal diffusivity is, the thinner the sample may be. And you should consider that at least a couple of millimeter sample thickness is needed. Typical samples are compact solids, like those metal or polymer blocks, but with the help of such adapters, which may be filled with powders, and a metal frame enforced sensor, which is used as a penetration sensor. Also, powders may be analyzed, and also fibers. And just by dipping a sensor in a liquid or a paste, you can determine also thermal conductivity of pastes and liquids. And the last two remaining instruments are dedicated to the analyzer of thin films, the so-called thin film analyzer, TF-LFA, and the thin film laser flash analyzer, TF-LFA. And when I say they're dedicated to measure thin films, this means there are very thin films in the nanometer to micrometer range. Films of hundreds of micrometer are no longer considered as thin films, and they are measured as bulk materials. The two instruments cover a temperature range from low temperature to 280 for the TF-LFA and 500 degrees for the thin film laser flash analyzer. So let's have a look on the thin film analyzer. It uses a transient hot wire method, so-called 3-omega method. And for measuring, analyzing a thin film, it has to be deposited on such a disposable sensor. It's very small. It has a side length of approximately 1 centimeter. And as the thin film has to be deposited on the sensor, you have no choice of the substrate. The sensor is the substrate you have to use. Once you deposited the sample on the sensor, you put the sensor in the sensor holder. This may be heated or cooled by liquid nitrogen. This measurement chamber is put under vacuum, and then the measurement is performed. Beside thermal conductivity, you get also specific heat capacity as a result, and depending on the instrument's configuration, also the Seebeck coefficient and electrical conductivity, and also the Hall constant. Those are parameters which are mainly of interest for semiconductors and for so-called thermoelectric materials. The last instrument I want to introduce is a thin film laser flash analyzer using a transient method, the so-called time domain thermoreflectance method. This is a modified laser flash method. In a usual laser flash analyzer, the light pulse has a duration in the range of micro to milliseconds. And this is a method, pulse, which is much too long to analyze thin films. And for this reason, in the thin film laser flash analyzer, we use a faster heating, a shorter laser pulse in the nanosecond range. In the usual laser flash analyzers, an infrared detector is used to monitor the surface temperature. This would be too slow for thin films, and we use another technique, the intensity of reflected light. So this is shown in this schematic drawing. You have a sample on a substrate, so you are free in the choice of substrate. Then you heat the surface of the sample by a short nanosecond duration laser pulse, while a continuous laser is irradiating the surface and is reflected on this first surface. And from the intensity over time, you get the information to calculate thermal diffusivity and thermal conductivity out of thermal diffusivity. In order to have a kind of a thermometer, the sample surface has to be covered with a thin gold layer as a reflective layer, and the reflectiveness as a function of temperature is known. So this gold layer serves as a thermometer. So those were the 6 instruments I wanted to introduce to you. Now let's talk about different materials and their structures. If you want to analyze isotropic materials, so materials with the same properties in all 3 space directions, like in this diamond structure, the life is very easy and you can use whatever instrument you like. If the materials are anisotropic, so that the properties depend on the direction of the sample, then you have to consider that this materials, the properties may depend on the direction. So this can be on a microscopic scale, a macroscopic scale, like shown in this example. So we have a layered structure, and thermal conductivity perpendicular to the layers will be certainly different than in the layer. This may also be a microscopic structure, so a crystal structure like shown for this graphite structure. Thermal conductivity in the sense of these layers is much higher than perpendicular to them. So whenever you are dealing with anisotropic materials, you must ask yourself the question, in which direction you want to determine the thermal conductivity, and then to select the instrument which is able to do so. So there are some instruments able to measure through plane thermal conductivity, others do the in-plane measurement, and the transient hot bridge gives overall thermal conductivity. Should also consider the material structure. If you are dealing homogeneous materials, it's very easy. If the material is inhomogeneous, so there is a resolution in space, then you have to consider that these grains may have different thermal conductivity from one to the other, and also to the matrix. So whenever you are interested in the individual thermal conductivities of the grains, you need a high resolution in space. And if you are interested in the thermal conductivity of the complete tile, then you should measure a bigger surface, or you have to do many measurements and build up a mean value and do statistics. Porous materials are special example for inhomogeneous material. Whenever you analyze porous materials, you will get the thermal conductivity of the overall system, so of the solid material, including the pores. And you will not get the value just for the surrounding solid. Let's see this in an example for polystyrene. Polystyrene is a polymer. In this compact polymer, the thermal conductivity is 0.17 watt per meter in Kelvin. But if you have expanded polystyrene, like this EPS, which is used for insulation and for packaging purposes, this material contains gas, and this gas will lower the thermal conductivity, and the overall thermal conductivity of this expanded polystyrene is much lower than for the compact polystyrene itself. So we may divide the material in different types. So insulating materials, like the already shown expanded polystyrene, or fiber, straw, wool, cork, and cellulose, for example, organic materials in general, have very low thermal conductivities. The application temperature is usually close to room temperature. The materials used for furnace insulation are an exception, requiring high temperatures. Polymers usually have thermal conductivities of much lower than watt per meter in Kelvin, and polymers are used mainly below their decomposition and melting temperature, which is usually much lower than 300 degrees centigrade. Ceramics have thermal conductivities strongly depending on their structure and composition. For example, porcelain has a quite low thermal conductivity of 1 watt per meter Kelvin. And nitrides may have high thermal conductivities of hundreds of watts per meter and Kelvin, like, for example, boron nitride. Ceramics may be used at low temperature, but also at high temperatures higher than 1000 degrees centigrade. Metals have high thermal conductivities, usually in the range of tens to hundreds of watts per meter and Kelvin, and the application temperature may exceed 1000 degrees centigrade as well. So whenever you consider to measure thermal conductivity, there are some criteria to be taken into account. First, the thermal conductivity range of your material. It may be in a low, in a mid, or in a high thermal conductivity range. And some method like Transient Hot Bridge and Laser Flash Analyzer may analyze all three of them, while the heat flow meters can analyze only materials with the lowest thermal conductivity range. Second criteria is the temperature range. Some instruments work close to room temperature or at low temperatures, others in a moderate temperature range, and mainly the laser flash and also the Transient Hot Bridge can go to very high temperatures. The third criteria is the sample size and the homogeneity of the sample. Some analyzers may analyze thin layers in the micrometer or sub-micrometer range, others in the millimeter to centimeter range, and mainly the heat flow meter can analyze samples in the decimeter range. Fourth criteria to consider is isotropy or anisotropy of the material and the direction of the measurement. Some methods measure through plane, others in plane or overall. And last but not least, whenever you want to purchase an instrument, the price of the instrument has to be considered as well. Heat flow meters and Transient Hot Bridge are the less expensive instruments, while laser flash analyzers are the most costly. So on the following slides, I summarized all these data. In the middle, you will find the instrument, in this case, a heat flow meter. In this upper bar, the different temperature range is from low to high temperature. On the left-hand side, the expected thermal conductivity, a low, a mid, and a high thermal conductivity range. And in this lower bar, the sample size varying from the decimeter to the micrometer and sub-micrometer range. So the heat flow meter is used in a temperature range close to room temperature for low conducting materials of a big size in the decimeter range. The TIM tester can go to somehow higher temperatures, covers a moderate temperature range, covers a low and mid thermal conductivity range, and needs samples in the centimeter to millimeter range. Laser flash analyzer cover all temperatures from low to very high. You can analyze all types of materials from low thermal conductivity up to high thermal conductivity. Typically, samples are in the centimeter and millimeter range, but with some special adapters, you can analyze also samples in the range of micrometers. The Transient Hot Bridge is used to characterize materials of all thermal conductivities in the low to moderate temperature range, and you may analyze samples of some centimeter size up to the decimeter size range. And the two thin film analyzers, the TF-A and the TF-LFA, are dedicated to samples in the micrometer to sub-micrometer range. They may analyze all types of thermal conductivities, but in a temperature range up to moderate temperature only. All these information may be found also on our website in a table where the instruments are mentioned, the parameter to be measured, the temperature range, and so on. So you can have a look on our website. So let's do a couple of examples. Let's first consider a polymer. Polymers are used in a temperature range, usually from room temperature to a temperature below the melting temperature, so 100 or 150 degrees. We can prepare quite big samples. We know that, the thermal conductivity of a polymer is usually in the range of 0.1 to 0.3 watt per meter and Kelvin. And our polymer is isotropic. So what instrument it would be the best suited for this application? The sample will be too small for a heat flow meter. It could be analyzed in a laser flash analyzer, but for the laser flash technique, you need to know also the specific heat capacity and the density. The sample preparation may be complicated because you need a very well-defined thickness of the sample. The main advantage is a broad temperature range of the laser flash analyzer, and this is not necessary for the polymer. And last but not least, the laser flash analyzer is a quite expensive instrument, which is not required in this case. You can use a much cheaper transient hot bridge, and perhaps you can also consider this, the TIM tester. So this was a simple polymer. Let's consider a so-called filled polymer or composite. Temperature range and sample size may be the same, but due to the filler, which is here in form of some grains inside the polymer matrix, this filler will increase the thermal conductivity, perhaps up to 10 watt per meter and Kelvin. And depending on the structure of the filler, the material may be anisotropic. So if you have, for example, a rod-shaped filler and you do an extrusion, then this filler rods will be directed in a certain direction, and thermal conductivity perpendicular to the plane will be different from the thermal conductivity in the plane direction. So which instrument should be considered? In this case, the laser flash analyzer and the TIM tester would be the best suited ones because they can analyze thermal conductivity across the plane of the sample. And depending on the sample preparation and on the special adapter available for the laser flash analyzer, also the in-plane thermal conductivity may be measured. Or if you are just interested in the overall thermal conductivity, then you can still consider the transient hot bridge. And a third example for polymer, a soft polymer, so a foam like shown in this picture. Temperature and sample size may be the same as before, but due to the fact that you have air-filled pores in this foam, thermal conductivity will be lower than for a non-pore containing polymer. And the material is considered to be isotropic. So in this case, the properties will depend on the sample compression. Here, in this case, the compressed sample will contain less air, less pores, or smaller pores. And for this reason, the thermal conductivity will be higher in this compressed foam than in the non-compressed foam. So in this case of such a foam, you could consider the TIM tester because a compression can be defined by the machine. And additionally, to thermal conductivity, you will get also the contact resistance. You can also consider the transient hot bridge using an accessory in order to control the pressure. And if you have bigger samples of 30 by 30 centimeter, you can also consider the heat flow meter. So those were 3 examples for different types of polymers. Let's have a look on 2 examples for ceramics. Ceramic may have high application temperatures exceeding 1500 degrees. Sample size may be the same as for the polymers. Thermal conductivity, depending on the material structure and composition, may vary from 1 to hundreds of watt per meter and Kelvin. And in this first example, the material is considered to be isotropic. So the HFM, the heat flow meter, will not be suited to measure this sample for all reasons. It does not cover the temperature range, neither the thermal conductivity range, neither is a sample big enough. The TIM tester has a limited thermal conductivity and temperature range, and sample preparation may be a little bit complicated because you need 3 sample thicknesses, and depending on the properties of the ceramic, this may be a little bit difficult to achieve. The transient hot bridge has a limited temperature range and does not cover the full required range. And so the laser flash analyzer is the only instrument covering this application and mainly covering this broad temperature range. A second example is a ceramic containing grains like shown in this example. All parameters may be the same than in the first example, but it's inhomogeneous and contains grains in the millimeter range. We saw in the previous example that the laser flash analyzer is the only instrument covering the temperature range, but the sample thickness usually used in laser flash analyzer is in the same range than the grain size of the grains in our ceramic. So you have to cut a lot of slices out of your sample and analyze all these slices containing big grains, many grains, smaller grains, or no grains at all, or very few grains. And then you have to calculate a mean value and do statistics, which may be a quite challenging task to prepare many samples. So perhaps you can consider a transient hot bridge. This requires bigger samples, so you need less samples to get a better mean value. The measurement is very fast. The sample preparation is quite easy, so that you can get many values to do statistics, many result values to get statistics, but the temperature range is limited and does not cover the complete range. An example is shown in this picture. So we have the sensor, which is placed between 2 blocks of this grain-containing ceramic. And the sensor may be positioned in different places. You can turn the blocks upside down and measure thermal conductivity on the different faces. Then you can plot the incidence over the measured thermal conductivity, and then you will get such a Gaussian shape, a graph. In this case, thermal conductivity is centered around 1 watt per meter and Kelvin. And in this example, 120 measurements had been done with a transient hot bridge. This will require perhaps a day's work. If you have to do 120 samples for the laser flash analyzer, this will take a couple of weeks of work. So this is what I wanted to show to you.